In this episode, we're going to be looking at Docker. I've broken this episode into two sections. First, we'll cover what Docker is at a high level and touch on the container workflow. Second, we'll look at a live demo of Docker in action. For you to really understand what Docker is and why it's useful, you first need to know what containers are. I discussed containers at length in episode number 24, but let's just recap for a minute with a focus on Docker. Personally, I think containers are best described when compared to traditional virtualization. With traditional virtualization, you start out with physical hardware. Next, you have the operating system, then the hypervisor. Finally, you have virtual machine images which interface to the emulated hardware provided by the hypervisor, thus allowing you to create many self-contained systems. This is well documented and understood, so let's move on to how this compares with containers. Containers actually have a similar foundation, starting with the hardware and operating system, but this is where things take a turn. Containers actually make use of Linux kernel features called namespaces, cgroups, and chroots, amongst other things, to carve off their own little contained operating environment. And the result ends up looking much like a virtual machine, just without the hypervisor. One really cool thing about containers is they do not require a full operating system, just your application and all the required dependencies. So if you happen to statically link your application, then the container would be extremely small, and the result is a lightweight container image that's easily portable. So in a nutshell, containers are a method for isolation via namespaces, resource control via cgroups, much like traditional virtualization, just without the hypervisor and operating system overhead. I think it's a fitting analogy to compare containers to traditional virtualization because even though the technologies are different, the end result looks very similar from an application's perspective. So now that you know containers provide isolation and resource control via kernel features, where does Docker fit in? Well, containers are really cool, but one of the major pain points in using them was the absence of a container standard and tools for easily managing the container workflow. This is where Docker steps in. By the way, I should mention that Docker did not invent containers, and the concept of containers, along with various implementations, has been around for more than 30 years. There seems to be a lot of misunderstandings about what containers are, how they work, and where Docker fits in. So I just wanted to break apart the various pieces and show where they fit. I should mention that Docker only works on Linux right now, because it uses Linux-specific kernel features. However, you can run Docker on all major operating systems via a Linux virtual machine, like we're going to do in the demo later. However, Docker is allowing people to standardize on a container format and getting the toolchain sorted out. This opens up a world of possibilities for other operating systems wanting to adopt a similar model. To really understand containers and Docker, let's jump back and focus on containers for a second, because I want to make sure this is clear. So we have our hardware and Linux operating system over here. Then let's walk through the four major pieces that make up Docker, along with what an example workflow would look like. First off, you have your Docker daemon. This sits on your server machines and accepts commands from a Docker client. This can either be a command line utility or an API call. Next, the Docker daemon talks to the Linux kernel via a library called libcontainer, which is also part of the Docker project. In the past, Docker was simply a wrapper around LXC, but since then, they've migrated to libcontainer. I should mention that the Docker daemon and libcontainer sit on the server, where the client does not have to. I'm just going to add this line to indicate the separation of the client and server. So what does the workflow look like? Well, the Docker client tells the Docker server to create a container using a specific image. The Docker server, by proxy of libcontainer, works with the Linux kernel to create a container using that image. The container is constructed using namespaces, cgroups, chroot, amongst other kernel features to construct an isolated area for your app in here. But where does your app and libraries come from? Well, this brings us to the fourth piece of the Docker puzzle, something called the registry. The registry is something provided by Docker, and it sits in the cloud. And it provides an area to upload, download, and share your container images. The registry is open source too, so you can download it and host a local version for private container images. Okay, so let's say that we wanted to push an image into a container. The client tells the server, use this image and pop it into a container. The server then heads out to the registry and downloads the container image, if it's not already cached locally. Then it takes that image and pushes it into a container. This is a pretty high-level overview of how things work. There are all types of exceptions that could happen along the way, but generally this is how it works. Let's just quickly recap the four major pieces that make up Docker. Docker is a daemon sitting on your operating system. There's a client application, either a command line tool or an API call. Next, there's libcontainer, which is used to talk to the kernel. Finally, we have the registry, which acts as a repository for all images, and it can either be one provided by Docker or a local version. Okay, so hopefully this jumble of lines makes sense. I just wanted to chat about the hype surrounding Docker for a minute. There have been countless news stories about Docker over the past 16 months. Personally, I think we're about to see a massive change in the way we think about virtualization. Let's just focus on this slide for a second. What happens when we're not required to use traditional virtualization software to get isolation and resource control? I imagine a state where we have both systems running. But what happens if there's a migration to containers? Personally, I see Docker as a disruptive technology. It has the potential to turn the virtualization industry upside down. All of the sudden cloud providers can see better utilization and performance because the hypervisor is gone. And what about private companies not having to pay for expensive hypervisor software? Docker is more than just software. It's a container standard, which might be used across other operating systems. It's interesting to take this idea and think about where the industry will be in, say, 3 to 5 years from now. Anyways, this is why I think keeping an eye on Docker would be a good idea. Docker actually has its roots in a hosting company called .cloud. Basically, from what I've read while doing research for this episode, .cloud uses containers internally to run customer code. And over time, they built up an arsenal of useful tools and know-how for working with and managing containers. In early 2013, .cloud thought their internal tools for managing containers would be useful to others, so they released them as an open source project called Docker. From there, Docker very much took on a life of its own. And in fact, if you fast forward 16 months till today, there have been lots of interesting developments in the container space. There's also an extremely fast-growing ecosystem around Docker, along with gaining major industry partners, the likes of Google, Red Hat, OpenStack, Rackspace, and Canonical. Google even recently came out and said they're running everything from Search, Docs, to Gmail inside containers. They're not using Docker, but they're starting to feed their lessons learned while running 2 billion containers per week into the Docker project. Sorry, I feel like I'm feeding the hype machine, but it's hard not to get excited about what the next couple years holds for containers. Just one more example about the deployment workflow. Think of a conveyor belt for a minute. At one end you have your developer boxes, QA, testing, staging boxes in the middle, and then production boxes at the end. Containers are so easy to use and package with Docker that they allow you to use the same images all along the way. There is no more "it works on my machine" types of problems. This has the developer community abuzz too. Anyways, the Docker journey is just getting started, and it will likely morph and continue to evolve. So something I say today will likely change tomorrow. Okay, that's probably enough diagrams and chit-chat. Let's jump into the demo. My hope is that you can follow along today. Back in episode number 4, we looked at using VirtualBox and Vagrant to quickly create virtual machines for testing. Well, it just so happens that there are Vagrant boxes which can be used for playing around with Docker. I highly recommend watching episode number 4 so that you can get this set up on your machine. All of the major operating systems are supported by VirtualBox and Vagrant, so no matter your operating system, you should be able to get this up and running. Let's get started by heading over to the Fusion GitHub repo where you can use Vagrant to download these Docker-friendly virtual machine images. I'm just going to scroll down here and copy and paste this Vagrant file into a file on my system where I can run Vagrant to download the virtual machine. Just watch episode number 4 if you're interested in getting this going for yourself. Okay, now that we have the Vagrant file on our system, let's run Vagrant up to download the Docker-friendly Vagrant VirtualBox and start it on our system. This is what's so great about Vagrant, is that no matter your operating system, you can all use the same virtual machine for playing around with Docker. So as you can see, Vagrant used the Vagrant file to download a virtual machine and install Docker. Next, let's run Vagrant status to verify things are good. Looks good, so let's log in by running Vagrant SSH. We are now inside our Ubuntu 14.04 virtual machine that has Docker installed. Let's just su to root and play around. I'm just going to show you the Ubuntu and Linux kernel releases so that you can verify your setup if needed. Now we're ready to start playing around with Docker. The first thing you probably want to do is run the Docker command without any arguments. This shows the Docker client's help message and command options. There's actually so many options that it scrolls off my screen. Let's just scroll up to the top of the output here for a minute. These commands essentially allow you to manage the life cycle of a container. things like building, sharing, starting, inspecting, stopping, killing, and removing containers. Let's just run docker version so that if you happen to come along and try this for yourself, you know what version I'm using. Looks like we're using the client and server revs 1.1.2. Let's just jump back to the diagrams for a second. At this point, we have the operating system up and Docker installed. Let's work through the example of telling Docker that we want to contact the registry, download an Ubuntu container, and run a shell inside that container. Let's run docker run -t, telling Docker to allocate a TTY -i. This allows us to interact with the container. By default, it actually goes into the background. Next, we need to type the container image name we want to run. So let's type Ubuntu. And finally, let's provide the command we want to execute inside that container. In this case, /bin/bash. I should mention that by default, Docker hits the public image registry, where you can actually go and search for pre-built images. There's actually some really interesting ones to play around with up there. Anyways, let's just tell Docker that we want to run a specific version of Ubuntu. How about 12.04 for example? After I hit enter, Docker looks locally to see if it already has the Ubuntu 12.04 image cached. If it doesn't, it'll head off to the registry and download it. Docker uses some really cool file system tricks which allows you to chain or stack file systems together. This is really useful for building base images and then tracking your app's changes. I plan on covering this in detail in a future episode. Finally, you will notice that the prompt changed. We are now sitting inside a shell in our Ubuntu 12.04 container. Let's run the ps command to verify that there's no traditional operating system running here. As you can see, there are only two processes, the shell and our ps command. You will also notice that the process numbers are really low. This is because we're using a namespace from the container which cars off its own little process area. Let me just go split screen here for a minute. In the top window, we're running our Docker Ubuntu 12.04 container image. Then down in the bottom terminal window, we're sitting on our Vagrant virtual machine where Docker is running. Inside the container, let's list the processes again. Then let's do the same outside the container. Notice how we have the container's shell as a child process hanging off the Docker daemon. Let's run an active process in the top window and rerun our process list down here. As you can see, the container thinks it has its own process list, and this is because our container process list is using a namespace. Let's exit this and clear things up. I just want to show you that containers actually have their own IP address too. I'm just going to list the IP address in the container and then the IP address on our Docker Vagrant virtual machine. The reason for this is that the network inside the container is also using a namespace. Finally, let's head back to full screen mode and exit the container. I should mention that Docker has its own method for displaying containerized processes. I just wanted to illustrate that when you're inside a container, your view of the world in terms of networking, mounts, processes, users, etc. is much different than if you were outside the container. Let's just rerun the Docker command. You will notice here that Docker provides the ps command. Let's try and run that. There is nothing listed here because we're not running any active containers. However, if we were, they would be listed here. What's cool here is that you can use the -a option to show all containers, including ones run in the past. Here you can see the Ubuntu 12.04 container we ran, along with the process which was executed, and some timing information. Docker actually has so many commands that you can play around with it for hours. I just wanted to show you a couple of things before we conclude this episode. The first one is the docker images command. This outputs a listing of the images cached on your machine. You can see that we have the Ubuntu 12.04 image here, and it was used to run our container a couple minutes ago. One really cool thing about Docker is the way it deals with file systems, in that each container you spawn gets a new file system which only holds the changes from its parent container, which allows you to do cool things like diffing our container's file system to see what's changed from the original. Anyways, I've probably talked long enough. This episode likely leaves you wanting more, as I've had many emails suggesting Docker as an episode idea. Docker is such a large topic that it's hard to cover in a short screencast format. So going forward, I hope to create several more episodes around Docker as I explore the topic in detail. One reader sent me a note suggesting that I create an episode series. Personally, I think this is a great idea, and what better technology to start with? So over the coming months, I plan on looking into Docker networking, orchestration, namespaces, C groups, and file systems. along with how to create images from scratch. My hope is that this will be an interesting episode series, so please stay tuned. Also, if you have any suggestions, please shoot me a note. Hopefully this episode gives you an idea of what the Docker project is, along with a starting point for where you can play around with it for yourself. Alright, that concludes this episode. Thanks for watching. If you would like to get notified about future episodes, please subscribe to my mailing list. You can do this by going to the Get Notified link in the header and entering your email address. Have questions, comments, or concerns about this episode? What about episode ideas? I'd love to hear your feedback, either good or bad. Shoot me an email, justin@sysadmincasts.com.